Good evening, everyone. It is the 14th of March. So it's the 12th there. It's the 14th of March, whatever year this is, 2024. Um, so what I wanted to do in this video is kind of just outline kind of everything I want to talk about in this series. Critique I got on the first video, which is 100% accurate, is that a lot of what made it into the video should have been prep work, and that's true. That was kind of problem is that the more I prepare, then the more I start overthinking what I'm talking about, and then I never end up talking about anything. Kind of, it's like a writer's block thing. That's the thing for me. Anyway, but I wrote out some notes here, and so I wanted to talk about these. So first of all, just I said that this is about seed phrases, and that's kind of true. So just very briefly, the idea of seed phrases. So we have a short phrase in English that you can memorize because you're like we talked about in the first video, your private key, the way it works, there's an elliptic curve, there's this generator point, and basically from the generator you can kind of just bounce around randomly on the elliptic curve, and the number of jumps is your private key, and the point you end up at is your public key. And you know this large random number might be hundreds of digits long, and memorizing that is hard. And so the idea was, well, let's have a phrase in English that we memorize instead of the key. So the basic algorithm, you start, you first have it's very counterintuitive when I started dealing with seed phrases. The whole reason that I made this video is because it was kind of like a huh moment for me when I started learning about them. I assumed that if you had the private key, you could figure out the seed phrase. That's not true. You actually start by generating the phrase itself. The way you do that, you generate 128 random bits. Then you add 4 check bits, so you checksum these with a hashing algorithm. Hopefully you know what that is, otherwise just Google it. But it's 4 bits that are a function of these 128 bits, and it has the property that if you get even one of these wrong, this should look completely different. Now with 4 bits, there's only 2 to the 4. There's only 16 possible choices here. But typically checksums are really long. But we take 4 bits out of a checksum, so we have 132 bits total, I believe. And then you encode that into 12 words. In theory, there's a bunch of different word lists you can use. In practice, there's only one anyone actually uses. There's 2,048 words. That's 2 to the 11th. So what that means is that, how do I phrase this? If you have 11 bits, you can encode 2 to the 11th. Here, let me just tell you what. So 2000, oh yeah, 2048, duh. I was 2048 is 2 to the 11th. What's 2 to the 11th? So there's 2048 words. So 132 bits. There's a number that's what this is. 132 bits. It's 132 ones and zeros, but that refers to a number. There's 2048 words, and so each word basically is 11 of these digits. So it grabs 11 of those bits. You can think of it as the first word is just, well, we take those first 11 bits and pretend it's a number between 0 and 2047, or 1 and 2048. 0 and 2047, that's better. Which number is that? We pick that word, and that's the first word in your seed phrase, and so on. There will therefore be 12 words because there's 132 bits, and each word consumes 11 bits, so 132 bits divided by 11 bits per word is 12 words. So it's a 12-word phrase. And then weirdly, what you do is you actually take the ASCII text of the phrase. So you don't take these bits, you take the ASCII text of the phrase, and you hash it using a password hashing algorithm. No, talked about these hashing algorithms up here. It's the same basic idea. the idea is that like you get one little letter wrong in this word and you should get a completely different byte string at the end. So for instance, when you store your password, so like you log into Amazon with your password, some websites actually in their database store the plain text of your password. They're not supposed to do that. What they're supposed to do is take the password and then hash it and then store the hash of the password. And this is in theory a one-way function. So from the password, you can figure out the hash. And so therefore they can check if a password is correct, but you shouldn't be able to, given the hash, figure out the password. Now, you also have to take the password and a bunch of random data that you add onto the end, and that's just another column in the table. So what they'll store in the table is like password or the hash of the password and then whatever garbage they added to it. And then whenever you ask, okay, your password is, password 123, it takes password 123 plus the salt, that's what it's called, adds that onto the end, then sends it to the hashing function and then checks, is this correct? The reason you add that random data is because if you just take a hash, well, people aren't, very creative in their choices of passwords. And so there are tables out there called rainbow tables where for all these, like, for all the most common passwords that people use, everyone knows what the hashes are of those. And so if you use a common password, which let's be honest, you do, then, even if somebody does a data breach and they in theory only have the hash of the password and shouldn't be able to figure out the original password, well, because of the way hashing algorithms work, now they know your password because they can just do a reverse lookup. They can say, okay, this hash, a bunch of random data, they can look at, they have a table and say, okay, what's the password? And of course, you use the same password for every website, so now they know all of your passwords. Anyway, so you use that byte string, the output of this hashing algorithm, as the seed for another algorithm that generates a tree of key pairs. And then there's some convention for which leaf in the tree is the key pair that the wallet software picks. All right, so again, this is sort of the short version, and then the rest of this I want to talk about what I'm going to talk about. So manner in which I'm presenting things. So I hate calling myself a mathematician, but I'm a mathematician. So my understanding of cryptocurrency, but especially seed phrases, is from the perspective of the mathematics because that's the locus of my understanding. I do genuinely think that thinking about things from the mathematical perspective is the simplest and most straightforward way to understand these things. And generally, when I learn a new piece of mathematics, I kind of go through the following process. I just try to gain intuition at first. I don't try to like really understand it, especially visual intuition. If you have a picture, a lot of examples, if you notice in the last video, every single time I would explain something, I'd always just say, okay, let me give you an example. So something concrete examples, especially pictures, those are always going to help you. Understanding why the math is true is a lot more important than being able to like formally prove that it's true. Proofs are important, but less important than understanding why the math is true. And then express the math. I think mathematical notation is not very good. And if you can express your math in code, that's always better. Now, really, again, I like math, and so I really am doing this just because I get to talk about math. So the seed phrases for me, seed phrases themselves are very important. I think people should understand how they work. But, from my perspective, selfishly, I want to talk about the math. And so the seed phrases kind of gives me an excuse to talk about all this math. So I'm going to do a different video about outlining sort of the subject of math in general. But of the sort of relevant math here, Generally speaking, the relevant math for cryptocurrency is a subject called number theory, which is what mathematicians call arithmetic because they want to get their grant proposals funded. Um, the goal of the seed phrase algorithm is to generate a tree of key pairs. Like we said, in order for that to make sense, you need to know what a key pair is. So that was the first video. And then I kind of got distracted. I was like, well, from here we can kind of just talk about how cryptocurrency works. And so I talked about that. So there's some other basic math topics that need to be covered. We talked about that point at infinity, and I think that's such a gaping hole in the explanation. I really feel like I should talk about that. But I started thinking about, okay, so in order to explain that, you need to understand projective geometry. And once again, in my head, it's a picture, and it's really simple. But understanding like if I just showed you the picture, I mean, I brought up that painting, and I was like, oh yeah, look at this painting, and then I forgot to explain it. Um, if I just show you a picture and don't explain the picture, then you're not going to get anything out of that. So I got to explain the picture. And then the problem is that like I started thinking through, okay, what all do I need to explain the picture? I'm like, oh God, I have to explain that, and I have to explain matrices, I have to explain all this stuff. And I'm kind of going back and forth about whether it's worth it. But this point at infinity is such an oddity, and it really should be explained. It is possible that you can understand this. You don't need to be a professional mathematician to understand this. It's not that complicated. However, in order to explain it, like I said, I need to explain a lot of mathematical machinery that if you're a mathematician, like I can just put these things on the screen. I can show you matrix multiplication, and every mathematician knows how to do that and doesn't need me to explain it. But if you're a non-mathematician in the audience, you're going to, or even if you, maybe took linear algebra in college, but you're, in your 40s now, you're like, oh, what was that? Oh, I think I remember that. So, however, another aspect of that, so matrix multiplication, that's kind of a rabbit hole. So my advice aside, if you want to learn math in general, linear algebra. Focus on linear algebra. Study as much linear algebra as you can. Learn as much linear algebra. Linear algebra and matrix arithmetic are more or less the same subject. And I will explain why if I talk about it. Learn as much linear algebra as you can. It's basically, okay, it basically applies to every single subject in math. And moreover, generally speaking, let's say you're studying graph theory and you're studying it from the linear algebra perspective, that's usually the best way to understand it. You're studying differential geometry, you're studying it from the linear algebra perspective. You're studying algebraic topology from the linear algebra perspective. You're studying, I don't know, chaos theory from the linear algebra perspective. That's always the clearest, not always, but generally the clearest and most straightforward way to understand it, and like the most generally powerful because it generalizes so well. And that's why I tell people to do linear algebra, because it gets you the most things right away. And moreover, it's not like it's a beginner thing. It's something that, the mathematicians at the highest level are going to agree with what I just said. So matrix arithmetic might be worthwhile purely on the improve your fundamentals justification. And also, if I explain some linear algebra, you'll immediately see why you learned all this weird, like, why are we doing this y equals mx plus b stupid nonsense in school? Because what you're doing there is actually like really basic rote linear algebra. And the reason is that so later when you learn linear algebra, you have some context. Okay. Also, another reason why I would talk about this projective geometry stuff is that if I explained it, I think even the majority of people who are otherwise like mathematically literate what I would explain would be new information. And so I think maybe on those grounds it's a good idea. I'm still undecided on this. I think as far as mathematical literacy goes, so there was a sub point here that I didn't mention, which is that projective geometry has a lot of other applications. And this is where I was like, oh, rabbit hole. Because, for instance, if you, I could, if I go and explain some projective geometry, right from there, I can start explaining like not general, special relativity. I can start explaining. What else can I explain? Oh, I could start explaining like 3D rotations with quaternions, and I could explain this like really simply. And it's like, you know, and the way that my brain works, I am gonna go into those territories because I'm me. Um, and that's kind of off topic, but not really because everything's connected to everything else. And also, like, whenever you learn a new thing, if you can look, like, oftentimes now, like, I'll open a random book about, like, I don't know, data science, and I'll see some formula that looks super arcane, but I look at it and I immediately see the structure. I'm like, oh, yeah, I know what that is. Um, and I don't have to, like, really dive deep into it because I can look at it and just immediately relate it to something that I've already studied a lot. And so being able to look at something new and immediately relate it to something you already understand, that's going to really help you out a lot. And also, I want to talk about it, and it's my channel, but this might just be another series. I don't know. Modular arithmetic. This is not optional. We have to talk about this. The first question, how do we do division in clock arithmetic? So I mentioned that, like, division is this idea that comes from geometry where we have a length and we want to divide it into n pieces. But I said that you could do that in a discrete space. And like, okay, so, with mod 7, you could just solve that in your head. But even with a mildly big number like 7727, what's 1 over 87 in that space? Well, you don't want to just guess and guess every single number and check. You want some way to do this very quickly. That's sort of more structural and algorithmic and illuminating. And that does exist. It's called the inverse Euclidean algorithm. And that'll probably be the next video. So, here's an obvious question. What's so special about prime numbers? That actually I might be able to explain right here, which is that, a prime number means that it doesn't have any numbers smaller than it that divide it. So there's no number smaller than 7727 that divides 7727. So what that means, a better question is, if this number is not prime, why would this not work? So let's say we're doing mod 8. Well, the problem is that what's 1 over 4 mod 8? Well, if we look at the orbit of 4, so we say 4 times 2, 4 times 3, 4 times 4, etc., what you'll discover is it goes 4, 8, 12, 16, 20, 24. And mod 8, it just goes 0, 4, 0, 4, 0, 4, 0, 4. So if you have a number that's not a prime, what ends up happening is there are numbers that are smaller. So, if this was a number that wasn't prime, like 8, if a composite number, that's the word. If this is a composite number, well, it has divisors. And those divisors do not have multiplicative inverses because you start multiplying them and then they hit the modulus and then they just cycle back and they never get to 1. So prime numbers have this special property where, because nothing divides it, you do this multiplication and you never will hit 7727. Because, if you had 87 times something was equal to 7727, and 8n was less than 7727, well then 7727 would not be a would not be a prime number. And then there's there's some, I'm kind of hand waving, but there's some subtlety here. Like, I've implicitly assumed something called the uniqueness of integer factorization, which is a non-trivial assumption that needs to be proven. So Anyway, why is it that division? Yeah. So application. Okay, here's another application which I probably will talk about. This would be something I stole from Norman Wildberger. He has a playlist called Boolean Algebra and Circuit Logic or something like that. It's an excellent playlist. And basically, with Mod 2 arithmetic, it turns out you can do formal logic and write it all in terms of algebra. Um, Now, I think this is more than justified to go and divert into this purely on fundamentals grounds because there is nothing more fundamental than understanding logic in math. There is nothing more fundamental than understanding logic, and this is the best way to understand logic. And it gives us some like hands-on experience with modular arithmetic. So I think like 95% chance I'm going to do this. Okay. And then maybe some basic group theory. I don't know. Yeah, yeah, I have to teach you some basic group theory. Um, all right. So, you know, I am going to code stuff. Probably the next video will have some code. Probably should stop talking too much about the math and get to the code, but I like math, so tough. All right. Next video will probably be the GCD algorithm and the inverse GCD algorithm, which is how we do modular division. And then from there, we can say, okay, what's the, what are how do we do division in modular space, or modular space is a different thing. In these Z modules, that's the correct term, is a Z module. And then maybe we can do this diversion into formal logic, which not sure. All right. See ya. Bye.